We said in the previous video that while it seems intuitive that an estimator with no bias or very small bias is generally good or preferable, we did see examples, or one famous example, Basu's elephant, where an unbiased estimator was not particularly good. Now let's consider another example. So if we have a random variable q, which is normally distributed, mean, mu, variance, sigma squared. If we assume that we know the variance, we know sigma squared, but we don't know the population mean mu, we want to estimate it from samples. So what we do is we draw a load of samples from Q. So I observe Q1, Q2, Q3, up to Qn. Well, it's easy to show that if I pick any one realization of Q, Q1, then it's an unbiased estimator for the mean, mu. It's not very good, though, because if I wanted to estimate the income, the average income across a country, I could measure one person's income and assume that that's representative. Well, on average, I'd be right, but there'd be a lot of variation around that. It seems obvious that a larger sample would be better. So maybe I pick two people and average their incomes, or in this case, I average Q1 and Q2. Still unbiased. So both of these are different unbiased estimators, but I think intuitively you would know which is better. You'd say one of them is only using one bit of information, Q1. The other, I'm using information from Q1 and Q2, so I'm getting a better picture. And in general, if I just add up n observations and divide by n, that, again, intuitively, I should think is even better again, because I'm using n bits of information. But I can also do other things. Now, I know that a normal distribution, the mean is the same as the median. So if I want to use all n bits of information, I could add them all up and divide by n, or maybe I could take the median. Or maybe I could do some weighted average. So instead of just adding Q1 plus Q2 plus Q3 and so on, I take Q1 plus 2Q2 plus 3Q3 plus 4Q4, divide by the sum of those weights, which is 10. That's also unbiased. So already I've written down 5 different unbiased estimators on this page. Just because they're all unbiased doesn't mean that they're all equally good. The question that we want to ask is, are any of them better or worse than others? So intuitively, we'd think if we're getting information from a larger set of observations, that should be better than one that doesn't use all of the information. But for example, the sample mean and the sample median both used all n observations. But is it the case that one is better or worse than the other? To answer this, we need to formalize a bit mathematically what we mean by better. So what we're really talking about, if we're comparing two things with where I know the bias, ideally unbiased, how variable are the observations? How variable would estimates be around that expected value? Because what we saw with Basu's elephant was that we had a case that was on average right, but the variance was huge. It was often wildly wrong in one direction or the other. So let's calculate the variance of this estimator, theta hat. Now, we'd ideally like lower variance estimators, that it'll give us not just an idea on average what the true parameter value is, but a bit more certainty about that. So except in some really contrived cases, we're never going to know the value perfectly. So we're never going to have zero variance in anything but a very trivial problem. But surprisingly, we can actually put a lower bound on the possible variance of an estimator. And we can assess, if we have an estimator, we can often calculate how close to that variance, that lower bound, it is. So we'll start with a single parameter random variable x, which I'm assuming it's continuous, so it has density function f of x given a single parameter theta. If I get a set of observations, x1, x2, up to xn, then I can write down the likelihood, and hence the log likelihood of my sample if I knew the parameter. Now, the derivative of the log likelihood with respect to the parameter is what we call the score function. So I've denoted it here as v, and the score of the sample given the parameter is just the derivative of the log likelihood with respect to the parameter. Now, we could easily show that the expected value of the score at the true parameter value for theta should be 0. And we do this just by calculating the expected value of v, which is the expected value of the derivative of the log likelihood. So I know how to differentiate a logarithm of a function. I get, well, 1 over the function times the derivative of that function. Now, of course, I can then just introduce this and integrate out, because the expectation is the integral of something times its own density function. So when I work this out, I'm just left with the derivative of the integral of the likelihood function. But the integral of the likelihood function has to be 1. So that means that the expected value of v, the true parameter value, is the derivative of 1 is 0. Now, I've been a little bit slack with notation. I've just drawn a single integral sign here, whereas, of course, x here is an n-dimensional integral, where I have n observations. So really, that's the integral of the integral of the integral n times. But the same argument holds. I've just avoided some messy notation. The other thing is, I've maybe, for those of you who are pure mathematicians than myself, you may have noticed I've obviously pulled a derivative through an integral sign, which can only be done under certain regularity conditions. In every case, pretty much you will see that is valid, but if you really wish to read up on exactly the validity of that, feel free, you won't find it in these lecture notes or slides. This brings us to the concept of Fisher information, which is just the variance of this score function. I haven't quite justified it here, but alternatively, we can calculate the variance of this score function just by working out the negative of the expected value of the second derivative of the log likelihood function. This is just a relatively simple consequence of the chain rule, acknowledging that the expected value of this score function is 0. So what it does tell us is, well, the name makes sense. It tells us how much information about the parameter value there is in the sample. Because if I have a large amount of information, that if I try to change my belief around what theta is, I'm going to have a big change in the likelihood that if I'm in the right neighborhood and I say, well, maybe theta's not around here, my likelihood function will drop off very quickly, and I will say, no, your new idea is a lot less likely. Versus if I have very small amount of information, I might think I'm in the right neighborhood for my estimate of theta, but if I try something that's very different, maybe the likelihood doesn't change that much, and I'm left with a situation where I say, well, I think it's about in this neighborhood, but I'm not certain. I could believe values much larger or much smaller, versus high information. Large information means I'll see big changes in that likelihood if I start to move around my belief around theta. So we'll see this more and more in subsequent videos, but you can think of this by being how much information about the parameter value is contained in a sample that we have, and this is tied to changes in the likelihood. So we're coming back to likelihood theory again, which we introduced a couple of weeks ago in the context of maximum likelihood estimation. Also, it's this guy again.